Hey everyone, and welcome to another Chem Q&A. In today's session, we'll be discussing the common questions students have in Unit 3, Area of Study 2. Let's get into it. So the first question revolves around rates of reactions. And students always ask, I'm writing down frequency of collisions, proportion of successful collisions, and I've memorized the explanations, but I have no clue what they mean. What do these words actually mean? So to take a step back, we know that when we're dealing with states of matter, surface area, concentration, and pressure, all of these affect frequency of collisions. When we're dealing with temperature, they affect frequency of collisions and the proportion of successful collisions. And then finally, with catalysts, they just affect proportion of successful collisions alone. So we know the explanations, but what do they actually mean? Well, starting off, frequency of collisions is easy. How often do particles collide together? The word successful has two criteria. Number one, do the particles collide with enough energy to overcome the activation energy? And number two, do they collide in the correct orientation? So basically, of those particles that collide, what percentage of them will actually be successful? So to understand what these words mean, let's build an analogy around this. So let's say that I'm throwing darts at a dartboard. And every time a dart hits the bullseye, that is considered a success, right? A successful collision. And let's say that on this dartboard, the chance of a dart hitting the bullseye is 10%, right? That is our proportion of successful collisions. So if I want to increase the chance of a successful collision, I have two methods up my sleeve. Number one, I can simply throw more darts at the board. So if I was to throw them by hand, I might only be able to throw 20 darts at the dartboard. And if only 10% of them are ever successful, I'll only have 2 successful collisions. But if I get a machine to start throwing darts at the dartboard, it can throw 100 darts. In other words, more frequent collisions. Of those 100, 10% will still be successful, meaning you've got 10 successful collisions. So this is how increasing the frequency of collisions can increase the number of successful collisions. Second, if we don't want to increase frequency, the other thing that we have up our sleeve is proportion. In this case, I'll still keep throwing darts at the dartboard by hand, but this time we're going to increase the size of the dartboard itself, such that my chance of hitting the bullseye is now, for example, 50%. So now, even though I'm throwing the same 10 darts, if 50% of the collisions are now successful, that means I have 5 successful collisions. So this is the interplay between frequency of collisions and proportion of successful collisions. One relies on just more particles colliding and the proportion staying the same. The other one says, irrespective of how many collisions happen, what's the likelihood it will be successful? So these are the two things at play, and hopefully that explains what we mean by frequency and proportion of successful collisions. So on to our next question, and now we're bridging the gap between rates and equilibrium. Students always ask, how do I know when to write a collision theory answer and when do I write an LCP answer? Sometimes I write an LCP answer and my teacher marks it wrong, saying I needed to write collision theory. What's the difference? So this is a classic mistake students make, right? Most of the time they're not even aware that there is a difference. So let's break it down. First of all, collision theory has everything to do with rate, right? How quickly a reaction happens. So this is where you're going to be thinking, your frequency of collisions, proportion of successful collisions, etc. LCP, on the other hand, is equilibrium. This is concerned with extent of reaction or the yield you get from a reaction. We're worried about how much product we're getting, and we don't care how long it took to get there. So that's the difference between rate and extent. Rate is about time. Extent is about the amount of product that you end up getting. So when you're answering equilibrium questions, it's very important to figure out which one the question is asking you about. And we'll show you why that's important. Take a look at this past VCA example, pause, and see if you can answer it. So let's have a look more closely at what's going on here. First of all, we can see an equilibrium equation, and the question's asking us what happens to the rate of the forward reaction and what happens to the concentration of NH3. So everyone naturally sees the equilibrium arrows and puts their LCP hat on. They're going, okay, there's a temperature increase, so that means LCP wants to favor the endothermic reaction, which in this case is a backwards reaction, and that shifts equilibrium to the left. So what that means is a backwards reaction is being favored, meaning the amount of ammonia, NH3, is going to go down over time. So everyone gets that part. But then when they come to the forward reaction rate, this is the critical mistake people make. They say the backward reaction rate has been favored, so that must mean the forward reaction rate went down. It is decreasing. That is incorrect. So let's explore this. First of all, the word favored just means one reaction is happening faster than the other. So if the backward reaction is favored, that means the backward reaction is happening faster than the forward reaction. But it doesn't tell you about the absolute rates of both of them. For example, both reaction rates could have gone down, but the backward reaction rate went down less than the forward one, so it would still be faster. So this is why favored is a comparative term, but not an absolute term. So therefore, how do we figure out what happened to the forward reaction rate? Well, it's got the word rate in the question. And what explanation do we use for rates? Collision theory. What happens when you increase temperature? You increase average kinetic energy, frequency of collisions, proportion of successful collisions, and therefore the rate should increase. So if you increase the temperature, the forward reaction rate should also increase. So that is why the forward reaction rate increasing and ammonia decreasing is our correct answer. Now this takes a bit of time to understand because we're saying the backward reaction rate is favored by LCP, but the forward reaction rate is increasing, and it comes down to understanding what the word favored means. So now you're in the know, make sure not to be that student on the exam that thinks rate is the same thing as yield and LCP. They are completely different explanations. Know which one you want to use. So our next question is also around equilibrium, and it's how do we know when the value of K, the equilibrium constant, is changing using Le Chatelier's principle? How do we know when a shift in LCP actually changes the value of K? It's a really good question and one which I think a lot of students think they know broadly, but they don't actually know the specifics. So let's get into it. Firstly, let's define a couple of terms. First of all, the equilibrium constant is a ratio of products to reactants at equilibrium. It's always at a specific temperature and it's specific to a particular reaction. Secondly, we know that Le Chatelier's principle describes what happens to a reaction when we change something about it. It causes a shift in the reaction. The key thing to remember here is that there's only three things that can ever change the value of K, the equilibrium constant. 1, multiplying the coefficients by a factor. 2, reversing the equation. Or 3, changing the temperature of the reaction. So most people are familiar with the first two, right? You know that if you multiply the coefficients of an equation by a factor, the way you get the new K value is you have to raise the old one to the power of the multiplying factor. We know that if you reverse an equilibrium reaction, the way you get the new K value is by taking the reciprocal of the original K value. Be careful not to get confused with your delta H rules here. They're different for equilibrium, but most people are comfortable with that. That leaves the final one, which is temperature. So why is temperature the only LCP change that changes K and not, say, adding a reactant or product or changing the volume of a system? Well, let's take an example, okay? Let's say that we have an equilibrium constant that is 4. So products divided by reactants equals 4. And let's say at equilibrium, we have 8 products, right? Concentration, whatever, and we have 2 reactants. So it's at 4. Now let's say we add some reactant into the mixture. What does LCP predict? When you add a reactant, it wants to shift to the right in order to produce products. So that means we are no longer going to have 8 products. We might have 12 products, for example. Now we also know our reactants are going to increase due to partial opposition. Yes, some of the reactants will be consumed, but some of it will still stay behind and therefore be higher than before. So maybe now we have 12 products and 3 reactants. Notice how the concentration of the products and reactants has changed. There's been a shift, but the ratio, 12 to 3, is still 4, which is our original equilibrium constant. So here we can see the value of the equilibrium constant actually hasn't changed. The same thing happens with volume changes. There is a shift in LCP, but the ratio stays the same. So why is temperature the only thing that changes the value of K? Well, remember, when we increase or decrease temperature, What we're doing is we're changing the frequency of collisions and we're changing the proportion of successful collisions. We're changing the very stability of the reactants and the products themselves. Remember, with LCP explanations for temperature, you need to talk about exothermic and endothermic reactions. Both of these reactions have different activation energies. And therefore, if you increase or decrease temperature, the proportion of successful collisions is not equal between exothermic and endothermic reactions. This is why when you make temperature changes, you change the very stability of the chemicals themselves, and at equilibrium, they want to have a different ratio than before. It's a very complex topic, but hopefully that gives a simple overview about why temperature is the only reaction condition that changes K, and volume changes and reactant and product changes do not affect the value of the equilibrium constant.